is everyone today? We are starting much later today than last week for some reason. Okay, let me just start with a review. So at the end of last class, we talked about partitions. So if you partition this class into those who are late and those who arrive on time, then that consists of the whole class. Actually, there are three scenarios. One is you arrive on time, which very few of you did today. Second scenario, you arrive late, which many of you are starting to come in. Third scenario is you're absent today. So we can create these three partitions. So we talked about partitions. If, say, there are two partitions only, late and on time, then that means if you're late, that means you're not on time. If you're on time, that means you're not late. That means these two sets have nothing in common. So you're either late or you're on time. If there are two choices, two partitions. So when we combine these two, it's the entire set or the whole class. So if you extend this to three scenarios, on time, late, and absent. Then what do we have? We still have the same property. On time and not on time, nothing in common. Absent and on time, also nothing in common, right? So when you have all three, then it becomes the entire set. So we look at examples before. And the key here is that for partition, definition for partition, is that it's non-empty subsets. That means we do not include the null or empty set. That's why the last one here, this contains a null empty set, is not a partition of A. Given that A is this. So given that this class, CSC165, say, consists of all the students who are registered for the course, then we don't consider empty set as a partition. Any questions about this? Okay, last class we did some practice. So basically we asked which of the following partitions of set of all integers, Z, there are four, actually the numbers there which you cannot see, but this is 1, 2, 3, 4. And we look at the example of 1 last time, and we said 3n plus 1, 3n plus 2, 3n forms a partition because it's multiples of 3. Within each multiples of 3, there are 3 possibilities. For example, 1 2, and 3. And then we repeat 4, 5, 6. So repeating 3 times. So since we have plus 1, plus 2, and also plus the 0, then that forms a partition. Okay, I know morning is not a good time, but it's as good a time as any. Okay, post it. If you're new, you were not here last time, but you just show up today, then you need to join this group. Where is it? Here's the group code. In case you were not here last time and you're new. So I just posted this attendance/quiz. So please answer it. And it's based on a review that I gave you today, just the beginning on the partitions. Very simple. So in the remaining cases here, we went over that for the first one, these 3 forms a partition. So I want you to answer this, which of the following are partitions of Z? This, this, and this. And it's multiple choose. It could be more than one, or it could be none of them. Okay, so basically this is what you need to fill out today. So your name, your ID, answer this is multiple choose. You can choose more than one. And then for this question here, number 3, if you say it is not a partition, that means you don't check it. You check none of the above, for example. Then you have to say, why not? That means give a counter example. And then last thing, just answer when were you in class today. And you submit. Okay, so go to it. And if you're new, then you need to install the Edmodo app. Okay, I'll give you 10 more minutes to complete. There's an attendance quiz. You finished? Good. I guess if you're here, that's more important. Just answer it. Anything you want, you can say. But it's taking attendance as well, so. And if you took my advice last week about studying the notes, then you already can answer these because you already did it before class. Do you have 5 minutes remaining? If you finish, just relax. Or you can read ahead on the notes. It seems this class doesn't like to print out the notes. In some classes, they'll print out all the class notes and then make notes on the notes. But you just have your notebook, which is fine. Oops. So did any of you read ahead on the notes before class today? Did you look at it yesterday, after class last week? Anyone look at the notes? No? One person? Okay, that's good. One's better than zero. It's infinitely better, actually. Just over 1 minute left, then I'll close the survey. Or the attendance, whatever you call it. So it's more important for you to just answer something and just put in and submit within 40 seconds. You have to submit within 25 seconds, the attendance. No, you have to go online. You have to go online for attendance quiz. Okay, maybe I allow him a few more seconds. Actually, time's up, but I guess I'll let him log in since he just came in. Can you log into Emodo, sign in the app, and yes, just fill it in right now. I mean, I give you a minute, I guess. Someone asked me last time, are they allowed to resubmit again? By default, it's set to off because I don't want you to submit multiple times, especially if you're submitting on behalf of somebody else, because you can use the same device and submit different names. Of course, I can check that, but so that's been turned off. And I just said if you need to, you just use another device. Okay, we have to move on. So can you just put your name, student number, and just submit?
Can I have one more minute? Just discussion about that.
Okay, 1 minute. Okay, why don't I just start? Today's lecture while we give second person just walk in another minute. Okay, so today we'll be covering proofs, proving the set properties. So first we look at the concept, what's known as element-wise set proof. Each element. So for example, we said for all sets A and B, and we have the intersection of the two sets A and B is a subset of A. So how do we prove that? So basically, what this means is element-wise, look at each element. So let's say, for example, an element X is an element or belongs to this set. So this set we're talking about is A intersect B. Okay, so given any element X that belongs to this set that we're interested in, so what does it mean? By definition, if we state this, X is an element of A intersect B, means, by definition, X is an element of A, and X is an element of B. So that was a definition given to you before. What this means. A intersect B, by definition, means X is an element of A, and X is an element of B. So we're just reversing the definition we gave you before. So we say, given that X is an element of A intersect B, that means X is an element of X, A, and X is also an element of B. So if that's the case, naturally, this is satisfied because X is an element of A is given in here as a requirement. So we are proving that X is an element of A. That means, now, we have A intersect B is actually a subset. That means all the elements in here is in A. So we call this element-wise set proof. We look at each element and show that this is satisfied. Okay, so in words, we go through this mathematical proof, you can say, and then we see, since all the elements in the set A intersect B is by definition an element in A, so that shows this is true. Okay, so this kind of proof actually requires a little bit of, I guess, English writing or language writing to indicate that the proof okay, it's been more than a minute. I guess I'll just close this first. Okay. Now the second claim. So we're talking about sets A and B again. So this is times separately A, set A, and set B, two different sets. The claim is that if A is a subset of B, then A is necessarily a subset of A intersect B. Okay, so if you look at the proof, we start with an element, X, that's in A. Okay, since we have this condition, A is a subset of B. That implies X is an element in B. Because all elements in A is also an element in B. Because A is a subset of B. So by this, A is a subset of B, we have this statement. X is also an element in B. So now we have X is an element of A, given, and we've shown here that X is an element of B. So now by definition, what does that mean? X is an element of A, X is an element of B. That means by definition, X is an element of A intersect B. So that's by definition. The conditions are, if this is satisfied, X has to be an element of A, X has to be an element of B, and these are true. So by looking at this one element at a time, X, we show that, okay, given this, by definition, if this is true, then X is also an element in B. So we have X element in A, X is an element in B, and by definition, X is an element in A intersect B. So that would be our proof. Okay, let's see how much you understand. A practice question. So now we have three sets, A, B, C. Those who are paying attention in class, those who are not paying attention in class, and those who are absent from class, maybe. So we have sets A, B, C. But this cannot be true, can it, if that's the case? If A is a subset of B, then what can that be? If we say A are people who are paying attention in class, then what can B be? So B can be those who are actually present in class. Right? You have to be present in class to pay attention. I mean, this is not broadcasting live. Right? So you have to be here physically to listen, to pay attention. That means you're actually present. And what can C be? If B is a subset of C, C then can be the whole class. CSC165. Okay? So A is those who are paying attention in class today, let's say. B are the ones who are present, like all of you here right now. Not all of you are paying attention, probably. Or cannot follow, I guess maybe I should refine it a little bit. And C is the entire class, that's all the people who register or sitting in the class, auditing the class. Okay, so what we're saying is if A is a subset of B and B is a subset of C, then A is necessarily a subset of C. That means if you're paying attention in class today, that means you're present today. And if you're present today, that means you are a member of CSC165. That's an assumption, I guess. We have other people, guests, sitting in as a guest. That means if you're paying attention today, that means you are taking this course for credit. Or you register in the course. That's what we need to prove. So we have sets A, B, C. So let's follow the same format. So previously we have this. So sets A and B, let's sets A and B given such that A is this. So what do we do here? Let's set A, B, C given such that, what do we fill in here? A is a subset of B and B is a subset of C. Right? That's given to you. What we want to prove is this. What's given to you is this if statement. If this is true and this is true. So we'll put that in. Okay, so where do we start? Okay, we will start with let X is an element of A. So this is given. And what? Okay, so we'll use this argument such that the first one we have this. Okay, so we start with X belonging to A. So this means X is an element of B. Is that right? Because A is a subset of B. And we have shown well, actually, we haven't shown here, but well, we can use the previous properties. X belongs to A, X is a subset of B, that means X is also an element in B, because it's a subset. So what's next? So we do the same thing now, right? Next, we use this condition and put this in here. So now we start with X is an element of B. And then we have the second condition, if this is true, and also B is a subset of C. B is a subset of C. So what does this mean? This means X is an element of C. Right? So we put down here, therefore, ... Therefore, X is an element of C. So to answer the completed proof, we said, since every element of A is necessarily in the set C, by this shows that A is a subset of C. Is that clear? So step by step, you just go through this procedure. We start out with, let X, element-wise, we start with an element X. It's an element of A. So we go through this. We know this is true. So if this is true, that means X is an element of B. And then we go through the same thing. If it's an element of B, then we also have B is an element, is a subset. Sorry, B is a subset of C. That means X is an element in C. Therefore, it's an element of C, and that means we're completing the proof. So if this question is given to you in a assignment, quiz, test, final exam, then you'll fill this in. Let X belongs to A. We start from there. And then we go and give the same statements that given this, that means X is an element in B. And then we can say, given X is an element of B, we get this, and then we say, therefore, this, and we complete this. So you can think of this as step by step. Just follow step by step instructions. So to remember the steps, look at the arguments, and then therefore, and then you complete your proof. Okay, any questions? It's pretty straightforward once you've seen it, but you have to do it yourself. All right. So next, let's look at the concept of equality. Set equality. When are two sets equal? So to prove, in order to prove that two sets, A and B, are equal, we need to have two separate proofs. First is that we need to prove that A is a subset of B, and we also need to show that B is a subset of A. So if both of these are satisfied, that means A and B are the same set, or at least have the same elements. Okay, so A and B are equal if and only if A is a subset of B and B is a subset of A. Okay, so if you look at this example that's given here, so previously we've shown this, right? In the first example we gave for proof, A intersect B is a subset of A. We also show that A is a subset of A intersect B when A, did we show that? Well, that's the claim, right? So we start out with this. Then we go with this. So what that means from what we just learned here about equality, since we have A intersect B is a subset of A, and then A is a subset of A intersect B, that means necessarily that actually these two sets are equal. If this condition is true. Because in the second case, we have a condition here. A is a subset of A intersect B when, or if that A is a subset of B. But if A is not a subset of B, then this is not true, or might not be true. Actually, it's not true. We can prove that. Okay, so the concept here is equality. When are two sets equal to one another? The condition is that they need to be subset of one another. So A has to be a subset of B, and B has to be a subset of A. And then A and B are equal. Okay, so next, maybe I'm moving a bit too fast for the morning. That's why I asked you to read ahead. And then if you have questions, let me just go back here, give you a chance. Any questions? Okay, the comment here, set equality is kind of confusing. Is that true? Let's just start with up here. Forget the example. Start with up here. Is this clear? The first part's clear? We're talking about two sets, A and B. When are they equal? They're equal if and only if that A is a subset of B, and B is a subset of A as well. If that is the case, then A and B are equal. That's clear, right? That's not confusing. So the example, maybe some of you will find confusing. We gave previous two examples here. So first is all general sets, A and B. We say that we prove that the intersect of A and B is a subset of A. And we went through the proof, right? So the proof was here. So if X is an element of this set, that means, therefore, X is an element of A. So we went through that proof. So now consider, instead of we're asking A and B two sets, are they equal? We're asking A intersect B. We can call that set C if you want. And A, are they equal? So is this set A intersect B, which we can call C if you want, is it equal to the set A? So it's equal only if and only if this is a subset of A and A is a subset of this. Right? By definition of equality. So in the second example, we said for any given sets A and B, this is general, if this condition is satisfied, if A is a subset of B, then indeed we will have this. A is a subset of A intersect B. So in a way, we're answering this. Given that we have two sets, A intersect B, if you want, you can call that set C. Of course, if you say equal here, we have to prove, but if you say given, that means we say this is true. So to make it less confusing, let's just remove that. So two sets, A intersect B and A. Are they equal? Or when are they equal? So for this to be true, we need to show A intersect B is a subset of A, and A is a subset of A intersect B. For equality, right? This is by definition. So we've shown that this is true. The first one is true with our first proof. So this is true. For the second one, in our proof, we prove that this is true if A is a subset of B. And this is the proof that's given here. So for this, this shows us this. If A is a subset of B, then this is true. So in this example, we said, we have shown this is true in the first proof, and then we show this is also true if we have A is a subset of B. Then we can conclude, are they equal? Well, these two are equal when A is a subset of B. That's what we say here. If A is a subset of B, then these two sets, A intercept B and A, are equal. Okay? I think most of you got it. If you pay attention, then you would understand. If not, then you have to catch up somehow. Any more questions? I hope it's less confusing now, the example here. If you're writing this down in your notes, then make sure you understand what you wrote and that makes sense to you. Okay. So next we're going to look at some algebraic properties. So properties, in particular, the algebraic ones. It is for sets. So let's start with a theorem, something that we say is true. Well, of course, we can prove it, which you can do. This is right here. We're trying to prove, the theorem says that two sets, A and A union B. So here we have A intersect B and A, right? But now let's look at A and A union B, or A or B. So we're saying this is equals to A. So previously we showed that these two are equal, but in this case we're saying this. So it's a new set. The set is A intercept A union B. This is one set. We're saying this set is equals to A. That means this operation, when we take A union B, we got a set. And we take A intersect that set, we'll get A back. Only A. So that's what we're trying to show, so we'll prove it. So to prove this, we have to show the left-hand side here, this set, is a subset of A. And also A, the right-hand side, is a subset of the left-hand side. So that's the definition of equality. You can prove that as an exercise. So this property here is called the absorption property. Okay, not much I can do on here. I cannot mark on this version. Anyways, so this property, A intersect A union B equals to A, is called the absorption property. That means when you take union and then intersection, you'll get the original set A back. So we have other properties given on your textbook, which is also shown in the next slide. So these are some other properties. So the first one I've shown you here is called the absorption property. So this is the first algebraic property I'm showing you. Other ones are here. We have commutative. That shows that A intersect B same as B intersect A. And similarly for union. Associative. So it doesn't matter what you put a bracket here or you put a bracket there. It's actually the same. So one of the property of sets is it is associative. It's commutative, it's associative, it's also distributive. So you can expand this. A intersect B union C is equals to A intersect B and then union A intersect C. So you expand it out. We call that distributive property. So in algebra, you have seen this. We're just applying these properties to sets. So not a single number, talking about a set of elements or objects. There's also identity. So if you take the intersect of A with the universal set, that means includes everything, you'll get just A back. If you take the union of A and an empty set, you also get A. So it's like multiplying by 1, you get the number back. Multiplying by 0, not multiplying by 0. Is there an algebraic operation? Plus? Oh yeah, okay, plus, sorry, good. If you plus the number plus 0, you get the number back. So that's identity. Multiplying by 1 or adding 0, you get the same number back. So it's the same property here for a set called identity. The operation results in the same set, in this case. We also have negation. Negation means it's negative, the opposite. So when we take A and the complement of A, which means everything but A. So together gives you the whole universe, universal set. So those who are in class is A. Those who are not in class is the complement of A. And together gives you this class. And again, these two, what this also means is that A and A complement forms the partitions of the universe, universal set. Which means, obviously, there's nothing in common between these two sets because they are partitions. We also have double negative. A complement and the complement of this result gives you back A. So you have seen this. You have seen De Morgan's law in high school before, but maybe not for sets. We can take the complement of this. Difference is that the intersect becomes a union when you expand what's within the parentheses here. So same for intersect, give you union, and then union here, you have intersect when you expand it. So that's called De Morgan's law. Absorption we already talked about. And the last thing that here, well, universal is also here. This is A multiplied by 0, you get 0. And then A multiplied by 1, you get 1. So the last one, given That means, like what I said here, given. Given means it's things that are given to you to be true. So any statements given in the hypothesis, actually not true, it's just a hypothesis. You can prove it to be true or not true. So before we go to break, let's go through an exercise. So we have seen some of these set operations from here and the proofs before. So given what we have learned from the old things you have learned already, let's try to prove a new property. Okay? So this is something that we have not seen. Let's see if it's true. Well, we say it's true, let's try to prove it. So given all sets A and B, so we have two sets, A and B, general sets. We want to prove that this is true. So it's an equality here. We have a left-hand side, which results in a set, and a right-hand side is another set. We claim the results of left-hand side and right-hand side sets are equal. So what do? Let's start out with the left-hand side on this A intercept this equals to what? What property you want to use? Set operation here. Which property? What do you want to do first? And tell me which property you're going to use. Keep in mind, we want eventually to show that this is true. So we have A intercept this, and we have A intercept this. So what do you want to show? So left-hand side is this, right-hand side is this. So somehow we want to get eventually to the right-hand side. So what do we need to do? So we know that A intercepts the same, A intercepts the same. We want to show basically that this somehow equals to B. So what's the first step? De Morgan. Okay? So De Morgan involves this and a complement, right? So if you go back here, De Morgan's law, A intercept B complement equals to A complement union B complement. So let's fill that out. So this is good exercise. So we'll use De Morgan. That means we'll expand this. So we get Is that correct? Or should we use something else? Sorry? I mean, is this line correct? Yes or no? going step by step. De Morgan, right? So we start out with this. We take the prime. So it's this prime. Intersect becomes union A prime. This is De Morgan, right? So is this the first step? It could be the first step. So what's the next step? Double negative. Or double negative here, right? So what's the third step? Distribute. So we have A you want to use distributive. Union so distributive A intercept, we have two things here. So intercept B, union A intercept. So that's what we have. A intercept B, union A intercept A prime. So what's next? This is what? So right here, negation. A intercept A prime is empty set, right? So negation. So what's next? So something union identity, right? Identity. So are we done? So this is equals to left-hand side. Sorry, right-hand side. We done? Right? Sorry? Can I show all properties?
You need to know them.
Do you need to know all properties? Yes, you need to know all properties.
In the exam.
In the exam, yes, you should know all the properties. It's not that many. And you know most of them. I mean, some of them, actually you know all of them. Just the name, you may not know the name, but or if you're really stuck for some reason, it's possible I can give you this table. But it's not that difficult to memorize this because it's intuitive, I think. Some of these you have seen already. Okay, so we're done with that. So the last one, we can also do the same thing. A union this, we want to show that this is true, proof. So we start out with the left-hand side, which is this, and then we expand it out. So this is what? This is distributive, right? Distributive, A union A prime, intercept A union B. So this is distributive. So now this is what? A union A prime gives you the universal set. From negation. Negation. And then commutative. We switch the order. U intercept this is equal to this intercept U. So this is commutative. First one. And finally, to get this, actually we can get it from here, but to get this is by what? So what is the last one? A union B intersect universal by what? To give you this. Okay, identity. A intercept universal gives you back A. So that's identity. So equals to this. That's the right-hand side. So done. Okay, so time for a break. So let's go for 10 minutes this time if we can, because we have quite a few things to cover. Okay, right on 10:30 on my watch, so 10:40. I will start again. Okay, it seems like 10 minutes is more like 15 minutes. We should get started. It's almost 15 minutes. Anyone who came late and not took the quiz attendance earlier? Okay, can you come up and put your name on here? So I'll give you some credit if you're late. Just write down your name and your student numbers. Come up here. Okay. Okay, let's get started. I set it to maximum volume already, almost. And your noise is obviously still louder. Okay, next is chapter 4 on functions and relations. This is something that I believe all of you have taken this in high school, or at least part of it. Because if the science track in Thailand, or wherever you come from, if you're supposed to have science background to be able to enroll in computer science. So you would have seen functions and relations in some form. So let's go look at something very simple. Two examples defining functions. Could be algebraic, or in this case, pre-calculus. That means you don't need to know calculus because it's just functions and relations. They're separate. Functions and relations, calculus, there's some similarity, but usually you start with functions and relations first. So here we have the notations here. F, and then we say G, two functions, we're mapping. I'll use the term map from one domain to another domain. So we start out with something in R, which is the real numbers. So we have the names, the domain, the input in this case, belongs to the real domain. We're mapping from one domain to another domain. So input mapping to an output domain. And that is the codomain. So we call this domain to a codomain, mapping from input to output. Okay, just a notation. Talking about for the function f. The rules specify f, in this case the same f, of x. X is the input. We'll map x into a domain, codomain called f of x, using this relationship, 3x plus 1. So we take input x, we do algebraic manipulation to get 3x plus 1, and this is the output in the real domain. So x is a real number, any real number. So it can be 1.2, 5, 6, 7, 8, 9, 10. No, actually cannot. 10 is not a digit. So just be careful. When I say 10, I mean 10, of course. So we're going to take that as input, which is a real number. We map it. And the output would be also another real number. Second example is for function g. In this case, we're mapping from integer domain to what's n? Natural numbers domain. And you can see from this, x is an integer. That means it can be negative, infinity, including 0 to positive infinity. When we square it, all negative numbers become positive. So basically we have the numbers, set of integers from 0 to infinity, which is a set of natural numbers. Okay? So components again, we have name of the function. F or G example. This name of the function. And then we put colon here, say function f, such that we have this. First is a domain, and then the codomain is the input, codomain is the output, and then we have the rule that will specify how we map the input to the output. And the key here is one and only one output. So each input maps to only one output and only one output. So that's the requirement or definition of a function. If this is not satisfied, then it is not a function. Function is mapping 1 to 1. If you're mapping from 1 to many, then by definition, it's not a function. So also make a note that here, all the elements in the codomain is necessary in output. So that means following these rules, you get an output. Following this, we get an output. All of these are output. But every element of the domain must be a valid input. That means we cannot put It says input has to be a real number. We cannot put a complex number in there, for example, because this maps real to real. We cannot put I in here, for example, complex number. And here, the input is a set of integers. So we cannot put a real number in here or irrational number in there. Okay? Every element of the domain, which is the input, must be a valid input. That means it has to belong to this domain. Okay, so this is all what this is explaining on this slide. So we have other ways we help you to visualize better. Because actually visualization is something that humans like to do. I mean, you come to class to visualize me teaching too, you can say. Or you may want to go back to e-learning. E-learning, I believe, only shows you this screen. So you're missing this, you're missing this, you're missing my expression. So it's not the same because this camera here trains to this only. So if you have used e-learning, you would notice you have this only. But we are developing other platforms. Another platform is called a MOOC. You know what that is? Massively online open course. Actually, our school has a MOOC. It's not officially rolled out yet. We're going to be adding some content. And the MOOC, by definition, actually means it's free. You have MOOC courses you can attend from other universities, like from Stanford, MIT, University of Toronto. They all have a MOOC. They would have a course on discrete math. So if you like, you can go register for a course in Stanford on discrete math, enroll free of charge, and complete it free of charge. The content will not be the same, but it will cover the same basic materials. They may have something more advanced, more theoretical. In our program, we don't emphasize as much theory because most of you will have problem with theory currently. But we do give you some theory, as you've seen from the proofs and so on. Okay, so anyways, other ways to describe a function, the rules, which talk about here. So this is a rule for function f, for function g. So let's say we start with two given sets, A and B. A consists of elements 1, 2, 3, 4, 5, which are integers or natural numbers, depends how you look at it. And B is also 1, 2, 3, 4, 5. So you can show by the proofs we've done earlier, A equals to B, right? When you look at it, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, A equals to B. Right? Yes? No? Maybe? Not sure? A equals to B? It's not a trick question, just a simple question. Yes, right? Because A is a subset of B, B is a subset of A. So A equals to B. You can do each element, 1, 2, 3, 4, 5. They're all in one another. Okay, so what we want to do is, we have a function f, the name of the function is f, and we have A mapping to B. So A is the input, and B is the output. So it's the same form as here. We haven't specified a rule yet. So we have this. Now, let's look at the rule. We want a set of order pairs, this. So how do we describe the rule? Well, one way to describe it is by a table. We start out with x is 1. The output, we want to map it to be 5. So 1 gives you 5, 2 gives you 2, 3 gives you 1, 4 gives you 2, and 5 gives you 5. So I'm describing the rule in terms of a table or in terms of set order pair. So these are other ways to describe the rule. In the previous example, we give an algebraic equation. But that's not the only way to describe a rule. We can describe it as an order pair, or in form of a table, or in form of a diagram. So we have two domains, A, 1, 2, 3, 4, 5, B, 1, 2, 3, 4, 5. These two sets are actually identical. But the rule says we'll map 1 from the input to 5 in the output. We'll map 2 in the input to 2 in the output. 3 to 1, 4 to 2, 5 to 5. So each input has one output, one and only one output. So that means this is a function. Note that it's possible to map different elements to the same output. That's not a problem. But each input maps to only one output, and only one output. Okay? So these are different ways to describe a function's rule. So we have order pairs, we have a table, we can also show it in an arrow diagram. Okay? Different ways to describe the rules for your function. The function being this. Okay. Before we practice, for those of you who like equations, can you give me an equation that will map this to these output? Can you put it in this form? F of x equals to what? And I can tell you right now, there's no single answer. There are multiple answers that can be correct. Because we have limited cases here. If you don't like this, we can look at this or look at that. Anybody want to try? Give me the equation in this form. F of x equals to something that will map this input to that output. X plus 4 for the first one, but not for the second one, not for these. It has to be the same function because we're mapping the rule. So all of these has to be satisfied in some equation. Is it possible? Maybe you say it's not possible. Okay, think about it. It's maybe not that obvious, obviously not that obvious. Let's go to something easier first. So now we can show this mapping like this. The key is 1 to 1. One input gives you only one output. Let's go to practice that. So here we have A consists of three elements, x, y, z. So now the function f, the function called f, has a domain of power set of A. So what is the power set of A? So something we covered last class, you may not remember. Power set means all the subsets, all the possible subsets, right? Including the empty set or the null set. Okay, let's get you to do some exercise. Volunteer on the left side, volunteer on the right side, come up to the board and write down the power set of A. We should get the same answer, right? So one person on the right-hand side, one person on the left-hand side. There are more of you here. But volunteer to come up to write down power set of A. You can choose your color. Come on, hurry up. Volunteer. Or do you want me to call a name? I mean, if you're bored, you want something to do, then come up and write. You could be sitting there sleeping or tired, so exercise. Come on. No? Okay, I'll call some names then, since I have some names here. Saran. Okay, pick a color. You can write on that side. The power set of A. Any volunteer on this side? If not, then I guess it's the person who came late. Okay, good. Power set of A. A is X, Y, Z. Power set of A. Someone want to give Sarah a hand? What is power set of A? Power set of A means all subsets of A. What are the subsets of A? Write them. All of them, all the subsets. Okay, so first you write this. Power set of A equal, and then you put open parentheses. That means it's a set. Okay. So what's the first element? X? Okay, fine. Put the set X. No, the set. Put in parentheses. Yep. Y, Z. Anything else? Okay, you're done. That's fine. Thank you. So this is that correct? Anything missing? I'm asking the whole class. Okay, keep going. That's correct so far.
The position matters. The position.
Nope. Nope. Let's write over here. Just next line, next line. It's not long enough. Okay. The only thing is an empty set. We don't need this.
Oh, okay.
Okay, thank you. Very good. Okay, let's give them a hand. So you can all exercise. Exercise by clapping your hands. Okay, so now we know what this is. The function we're mapping power set of A to power set of A. Domain, codomain. The rule is this. So now we have an algebraic expression. Okay, S is a set. S would be here. The function of S is you're taking S, you subtract off X, the subset X. So this is removing subset X. Is the output. Okay, so let's start out with maybe not tricky one. Start with this one. Let's start out with input is if capital S is this. So we put capital X in here. So let's start out with S is this. And then f of S is S minus this equals to what? X, subtract X, you got nothing, right? So this maps to that. Too bad I cannot draw in here. If I use my computer, I could, I guess. But this maps to this. That's the first one. Now, here comes the tricky part. What about the ones that, okay, with X is fine. X, Y, you take X out, you get Y. X, Z, you take X out, you get Z. X, Y, Z, take X out, you get Y, Z. What about the ones you don't have X? Like empty set, Y, Z, Y, Z together. What's the output? It's the same as the input. That's because you take it out if it exists. If it doesn't exist, that means it's the same. So this is just equals to S if this is not an element of S. Okay, so this maps to this. Y maps to Y. Z maps to Z. YZ maps to YZ. And again, keys. One input maps to only one output. So actually the answer is given here for the power set. All you have to do is just copy from here. Is that clear? Easy, right? It's not difficult, at least. I guess not difficult doesn't mean it's easy. But it's not difficult. Okay. What about this? We have A, same as before, consists of elements X, Y, Z. And now we have B, another set. It has elements 0, 1, 2, 3, 4, 5. So I want you to draw the arrow diagram for this function f. So the domain is power set of A, which is this. Same as before. But codomain is B. So codomain is not this. Codomain is B, which is 0, 1, 2, 3, 4, 5. And what that means, 1, 2, 3, 4, 5, is the number of elements in your set. You can have 0 elements, 1 element, 2 elements, 3 elements, 4 elements, 5 elements. So if you see the function, the rule is when you map input S, the function is number of elements of the set S. And the number of elements is an integer, is a natural number. Could be no element. So this has no element. This maps to 0. This has 1 element, 1 element, 1 element, 2, 2, 2, 3 elements. Again, not difficult, right? Just have to understand what this says. And then you map it, just draw this to 0, this to 1, this to 1, this to 1, this to 2, 2, 2, and the last one to 3. And that's it. That's all you have to do. Again, not difficult. Everyone okay? Okay, so let's talk about binary relations. So we start with functions. We show how you can define a function, how you represent a function. Functions have rules. So this relationship between the input and the output. Let's look at the binary relations. So we define binary relations with 2 domains. A is the input, and the output is codomain B. That means it's like before, you have A, well, not here, but like this. A mapping to B. Okay, domain A, codomain B. So the binary relation is any subset of A cross B. Remember what A cross B is? It's a Cartesian product. Defined by this. A cross B means it's AB. In this case, we define A is less than B. This is an example. So if you look at an example of binary relations, let's say A is a set of natural numbers from 0 to infinity. And B is also a set of, the codomain is also a set of natural numbers from 0 to infinity. So now we want to define the relations. We call it capital R, the relationship between domain and codomain. So what is it? We want ordered pairs A, B that is an element in A cross B, such that the condition is that this element A, the first order pair, is less than in value than B, the second one in the order pair. So this is additional condition. So first, this is your Cartesian product, just order pairs. So for example, since we're talking about natural numbers, the first one could be 0. The second one could be 1, 2, 3, 4, 5. Anything greater than 0. So that means 0, 1, 0, 2, 0, 3, and so on. Anything starts with 0, and then everything greater than 0. But 0, 0 is not. Because we have an additional constraint that A is less than B. 0 is not less than 0. Then we have 1, 2. So we start with all the zeros, all the ones, all the twos, all the threes, and so on. So this goes in infinite set because this domain and the codomain, they're both infinite. So we start with the first element, 0, as A. Second element is 1, and then third element is 3, and so on. So these are examples of an infinite set that will satisfy this relation. Any questions? So there's more notations here. We're defining relations, in particular binary, because there are two A and B. And the relation we're defining, you can say, is the rule. The rules for this function are given by this. So in other words, we cannot take this. We can also, like 5 comma 1, it's also not, because 5 is not less than 1. Because when you take the Cartesian product or the cross product, you'll get a very large number, 0, 0, 0, 1, 0, 2, and so on. 1, 0, 1, 1, and so on. 2, 0, 2, 1, 2, 2, and so on. So all of them until infinity. That's all A cross B. But we put in an additional constraint of this. The first order pair element has to be lesser value than the second in the order pair. So we cannot have these. So the resulting set is only this. Okay, so just more notations, relations. We call it R, and this is the relation. So here's a more, I guess, practical example, you can say. So let's define the domain as the current KMUTT students. So it could be undergraduate or postgraduate or even exchange students. And B is current KMUTT courses. So CSC165 is one of the current KMUTT courses, but there are others. Now let's have a relation R with this rule. So we have XY. So we have two binary, we have this, and we have A and B. It specifies that if person X takes course Y, so X and Y. So for example, I can say, I guess Saren came up earlier. We can put Saren's name here, and we can put CSC165 here. Because he's a current student, and he's currently taking CSC165. So this is one element in this output. So we can make use of that. Why? How do we make use of it? We can use this set theory to do scheduling. So how do we schedule such that you don't have a conflict in your classes? I mean, you take 6 courses, 4 courses, 3 courses, whatever, this semester, and there's so many students in KMUTT. So how do we make sure that whoever the student would not have conflict in the course they take? We can represent it in sets, and we can perform set operations. So there are different ways you can do this. Normally, they won't do this, but they could. Another example, so if the domain is a film actor that, well, appear in any films before. It could be Hollywood film, it could be Thai film, any kind of film. We can call that an actor. Then the relation with this rule, if the person X is in a film with person Y, so with another person. So by definition, if person Y appears in a movie, then that person, then we're saying Y is a person who appears in a movie. That means he's a film actor as well. Do you know what this is? The Kevin Bacon game? What is it? Anybody know? Well, then you can search. Well, you heard of 6 degrees of separation, right? Concept, social media. Means all it takes is 6 link to link you to anyone on this earth. So you're related to Bill Gates, just have to go through 6 person in between, maximum. So to prove this or show this is true, again, we can make use of set properties. We can do it in a set like this. Okay. So far, you cannot do that yet because I only give you examples, for example here, of relations. So these are relations. So we can define these relations and then we can do some operations. So just as a note here, because person Y is necessary, also codomain is also A. We don't need to say relation from A to A, because relation of A implies the codomains is also A. Okay, so here we don't specify B or the codomain because it's the same as the domain. So if it's not given to you, that means it's the same. And you can see in this case, it is the same. Okay, more arrow diagrams. So you all know what that means now, right? Arrow diagrams can be used to describe rules of function. So input A to domain is A, codomains is also A. So now let's set these relations. The relation is order pair Mn that are real such that m minus n is divisible by 3. So can someone help me to map? If A is 1, the input is 1, what's the output? 4. Someone said 4. So A is 1 here. The order pair Mn. So here by default is A. Codomain is also A, right? That means it's 1, 2, 3, 4, 5 for domain. 1, 2, 3, 4, 5 for codomain. Like this, domain, codomain. And someone said 4. So first element is here. If this is 1, someone said 4. So 1 minus 4 is minus 3. Minus 3, is it divisible by 3? Yes. So 1 will map to 4. Can 1 map to anything else? One can also map to 1. So now which one will you pick? Because if it's a function, one input gives you one output. So we have 1 minus 4 minus 3. So this is divisible by 3. We have 1 minus 1, 0. It's also divisible by 3. So we have 2 possible mapping. But we cannot map this to 1 and map this to 4 at the same time. One input gives you one output. So if I ask you to do this, do not draw two lines. Do not draw 1 to 1, 1 to 4. Only pick one of them. If you want, you can pick 1 to 1. And 2, again, you can map 2 to 2 or 2 to 5. 3, 3 to 3 only. 4 can be 1 or 4. 5 can be 1 or 2. Sorry, 2 or 5. Right? 5 can be 2 or 5. But you only pick one of the two possibilities. Otherwise, we're not defining a function. But note that here, we didn't say it's a function actually. We just said it's relation. So this is a case where, like I said, one input can map to more than one output. But if you do a multiple mapping, then this is not a function. We just define a relation. Relation can be one to many. We've shown before a function can have many to one, but a function cannot have one to many by definition of a function. A relation, we can have all these people knowing all the people there and vice versa. That's not a problem for relation. But it's like saying each of you can only be at one place at a time. So if you're attending this class right now, you can only attend this class. But you're also taking other courses. But at this time, you map to here. Okay, so you know how to draw these arrow diagrams, right? So next, we'll talk about one set arrow diagrams. Let's start out with A is a power set of 1, 2, 3. That means empty set 1, 2, 3, 1, 2, 3 together, 2, 3, 1, 3, 1, 2. So these are all the elements in the power set of this, which are elements of A. So A, you have these elements. So the rule we have, again, A is domain, A is a codomain in this case because by default. So X, Y are real numbers if X is a subset of Y. So what do we have? Empty set maps to everything. Because an empty set is a subset of anything, everything. Right? So empty set is a subset of this, empty set is a subset of this, subset of this. Empty set is a subset of any set. So you see the arrow points to all of those. So now 1 is a subset of 1, 2, 1, 3, and 1, 2, 3. 2 is a subset of 1, 2, 2, 3, and 1, 2, 3, and 3, and so on. Anything missing? Anything missing? Before you answer that, when we say one set arrow, we mean, it's fine notes here. The domain and codomain are the same set. That's why we can map A only because A is a domain. A is also a codomain. So we can say domain is this, and then we can map this to codomain, which is also in A. So if this is not the case, we cannot use one set arrow diagram. So now, again, go back to this. Anything missing in this one set arrow diagram? Have we considered all cases? Okay, there are two answers, yes or no. What's missing? Well, I want to ask you, anything missing, that means yes or no. Now this is saying what's missing in the solution below. That implies something is missing. It's a trick question. Something you haven't seen. Is this the entire solution? Okay, the answer is no, it's not the entire solution. So if you don't look at the diagram, and I ask you to map out the entire solution, what other things should be there? Anyone awake enough to answer this question? It's almost 12. You may be hungry, but... Sorry? Point to yourself. Very good. Because it's a subset. One is a subset of one itself. So I cannot draw it here, but basically we have to add things like, we have to draw an arrow to itself. Because we're talking about subset. So one is a subset of one subset, one set. So those arrows are missing. Okay, so this is, we use arrow diagrams to indicate also what we call state diagrams, which we might touch on later on. So one of them is this pointing to itself, 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 pointing to itself. Because X is a subset of X. Okay, so this I'll leave it for you to do yourself as an exercise. Okay, make sure you do this. It's not difficult. But the rule is this case, X intercept Y equals to empty set. Again, we have domains A, codomain is A. So you do the arrow diagram mapping. I can start with this one. Empty set maps to itself. But not this. One cannot map to one. because 1 and 1 does not give you empty set. Okay, I'll just give you a star. Like I said, this maps to itself. But the other ones, I can tell you, do not map to itself. Not according to this rule. It's actually pretty easy if you understand this rule. So in this arrow diagram, we are doing one-to-many, all possibilities, okay? So now we talk about function in the beginning. We talk about relations. So when is a binary relation actually a function? So one of the conditions, like I said, is if one input gives you one single output. Otherwise, it's not a function. Every input has one and only one output. This is when a binary relations is actually a function. So let's look at examples. So there are two cases here. Let's start with example 1. Domain is 1, 2, 3, 4, 5. Codomains are the digits 1 to 10. Sorry, numbers 1 to 10, not digits. Natural numbers 1 to 10. So you want to see which of these relations also give you a function. One of this is a function, and one of them is not. So you look at the mapping. Y is x squared. So we take, remember, x is the input, y is the output. So x is the input here. So that gives you a hint which one is not. Okay, if you cannot imagine it, then put in the numbers. So x is an A. Let's take 1. X is 1. What's y? 1. That's fine. X is 2. What's y? No element. Right? If x is, actually no, there is. X is 2, sorry, y would be 4. Okay, fine. X is 3, you get 9. X is 4, no element. 5, no element. So we have 1, 1, 2, 4, 3, 9. Not a function. Why is that? You need to have all elements of A, but it doesn't all map to B. So it's missing. So 4 and 5 do not exist in B. So the condition is has 1 and only 1. So if you look, you can look at the first part. Every input has 1 output. But 4 and 5 have no output. So in this case, 0 output. So it's not more than 1, but it actually has 0. That means this is not satisfied. It has to have 1. Only 1, but it has to have 1. But in this case, 4 and 5 have no output. So this is not. But the second one is 1, 2, 3, 4, 5 goes to 2, 4, 6, 8, 10. So the second one is a function. This is a function. The first one is not a function. Also, we can look at this case. One, 1, 2, 3, 4, 4, 3, 4, 5, 6. So this is the other case. 1 input has to give you 1 output. In this case, some give you no output. So this is not a function. But in here, in some cases, second one, 3 is input, gives you 2. 3 is input, gives you 4. So in the second case, the second relation gives you multiple output for the same input. So this is not a function. But the first one is 1, 2, 3, 4, 5. Each gives you a single output. So a binary relation is a function if and only if 1 and only 1 output comes from each input. Okay. So obviously, this is not a function. Each input can have multiple outputs. Okay, so single input, each input gives you 1 output. In this case, like I said, 3 gives you 2 outputs here. So this is not a function. The right-hand side is not a function. The left-hand side is a function, 1 to 1. 1 input gives you gives you 1 output. But here, 1 input, number 3, gives you 2 output. So this is not a function. Okay. We can also talk about what's called the inverse of a relation. We denote that by r to the minus 1. So the inverse is defined this way. Instead of xy, we have here, xy is the order pair for your relation. The inverse, yx. The flip is an element in the inverse of the relation. So let's look at an example. So A is 1, 2, 3, 4, 5, and B is alphabets, lowercase, A, B, C, D. So the relation we can define, one possible relation is 1A, 2C, 1D, 3B. So here, we can define this as a relation. Just another note that this relation we define is not a function because input 1 maps to A and D. This is not a function. But here we only talk about relation. So the inverse is simply, you flip it around. A1, C2, D1, B3. So that's how we define the inverse of relation. You just flip the elements xy to be yx. This is not a, okay, this example we give is not a function. That's all. A function is not one-to-one. If not one-to-one, that means it's not. You mean relation. You mean the relation is not one-to-one. Yes, in this case, it so happens the inverse is a function. Because each input gives you, each input only has one output. So this is an example, yes, that you can have a relation that is not a function, but the inverse is indeed a function. Yes, that's possible. And conversely, of course, the opposite is possible. You can have a function, say this is the function with this relation, but the inverse of this relation, which is this, is not a function. That's also possible. Just be clear, what is a function? A function means one input, each input maps to only a single output. If it maps to more than one output, one to A and one to D, then this relation is not a function. That's all you need to know. Function has that property. Okay, so here we talk about relation, not function. Relation, we define it this way. We said this is a relation. Then the inverse relation, we simply flip the order pair to get the inverse. So xy becomes yx. Okay, very simple concept. Inverse of a relation is the flipped order pair. So as you can see in this case, in this relation on the R side, we have 1 mapping to 2 and 4. Sorry, 7 mapping to 2 and 4. So again, this relation is not a function. It doesn't matter. We're talking about relations here. So now we want to map for the inverse. So what do we do to get the inverse? Well, there's another property here. In this mapping on the left-hand side, we see we have a two-sided arrow. That means we have the element 1, 4. We also have 4, 1. So if you want to be less confusing, you can draw two arrows. One this way and another one this way. But this is what this means. So here it's only 0, 3. It's not 3, 0. But in this case, we have 1, 4. We also have 4, 1. Okay, if you cannot visualize it, you can write it down. Let's start with 0. 0, 3. Only 1. So inverse of 0, 3 is 3, 0. You draw the arrow from 3 to 0. Then let's do the next one. 1. What does 1 have? 1 have 1, 4. So we draw the reverse of 1, 4 is 4 to 1. The next is 2. What does 2 have? 2 has nothing. 2 as the input has nothing because it's important to anything. 3 goes to 6. 3, 6. So the inverse is 6, arrow to 3. We can go through this 0, 1, 2, 3, 4, 5, 6, 7, complete all this, to get the inverse mapping. Okay? So remember this, if R function is this necessary function, and we already answered the question, no. And I would just, this last slide, find the inverse rule. Find the rule for the inverse with the rule of this. So in other words, given this equation, we want to find the inverse. It's very simple. So y equals to this.